let's do Newton's second law. Newton's second law says F net equals ma. You remember from last time that F net means sum of all the forces. We have another way of writing this. We write sum of the forces like that sometimes. So F net can also be written like that. This is just a Greek letter called sigma. The more proper way of writing it is something more like that. It just means sum. So it's the same thing. So you will often see the equation written like this as well. And I actually write it like that more often. But I wanted you to get the idea of what F net is. Because I say F net equals ma. But when I write it like that. M is mass, A is acceleration. And so if you remember, F is a vector. And so it means we're going to have to add forces together. If we have the sum of the forces, it means we're going to have to add vectors. And that's going to be the complicated part for this part today. So I have a step-by-step guide on this next slide. Although my PowerPoint is acting up today, so I'm sorry. It's my iPad. Here is the step-to-step guide on Newton's second law. You can write it down real quick, but I'll go over with an example. So pause the video now to write it down. Here's the example. 20 kilogram box is pushed along a frictionless floor with a force of 5 newtons. Find the acceleration. So we start with the free body. Always start with the free body. It should look like this. Because we have a box and it has mass, which means gravity is affecting it. So we have gravity down. It's on a floor, which means that there's a normal force. And there might be a friction force, except for this problem says frictionless. We're simplifying it a little bit before we do the next problem where we add friction in. And then there's also an applied force of Fn, so I just called it F1. And we're told to find the acceleration. So we draw this, and then we also need to draw our coordinate system. Great. Now comes that F equals ma part. I told you to do as out of habit to get it down. What we're really going to do is we're going to write it twice. We're going to write a wide t-chart, x, y, and we're going to write the sum of the forces, or the net force in the x direction, and then the net force in the y direction. We're going to write it twice because we're supposed to add the vectors, right? So we're supposed to add vectors, and if you remember how to add vectors, we had to add their components. And so instead of going like we did old school and converting them, all we need to do is look at the components separately. Look at the x side and look at the y side. And then at the end, if we have an acceleration in x and y direction, then we'll have to do Pythagorean theorem. However, guess what? The way we're going to set up all of our problems is so that we never have to do that at the end. We're always going to have acceleration in one direction. And we're going to do some tricks to make that happen. We're never going to have to do Pythagorean theorem. All we have to do is separate our components, and it's going to work out magically for us. It's going to be great. Okay, so on the x side, how many forces are there? There is one. Look on this free body. That's why you did the free body. There's only one force in the x direction. That's F1. So if we add them all together, you get F1, and that's equal to max. On the y direction, we have two forces. We have Fn up and Fg down. And so we have Fn up and then a negative Fg, that's down. And that is equal to may. But remember, or think about it, you have a box on a floor. This box is not flying up in the air and it is not phasing through the floor. Therefore, the acceleration in the y direction is 0. Pause for a second. Realize acceleration, it means we're speeding up or we're speeding up down. We're not speeding up, down, or up. We're staying in the same y plane. We're not moving up or down. We're only moving to the right. Therefore, ay is 0. And so we can rewrite this. Fn minus, let me get an eraser, sorry. Minus Fg is equal to 0. On the x side, we have F1 is 5. We have mass is 20. And we don't know what the acceleration is on the x side. And so we can go ahead and solve for it, and we get 1/4 or 0.25 if you simplify that. You can get it doing your calculator to double check me. Whoops, I wrote that weird. Meter per second squared. That's our unit. And so if we have AX equals 0.25 meters per second squared, and then we said that because it's 0, AY equals 0, that means we only have acceleration in the x direction, so we only really need to talk about it. That means this is our acceleration. And in fact, we're always going to set up the problem in such a way that we only have acceleration in the x direction, and so we never have to really worry about that second part. We're always going to set it up so that this becomes 0. Once problems start going in other directions, I'm going to show you some tricks to help that happen, to make it always that case, that there's only acceleration in one direction. So that's another acceleration. All right, let's do another one. We have a box pushed along the floor, but this time it has friction. So we're going to set the free body, Fg, Fn, force forward, frictional force back. And I don't really know as of now whether or not one's bigger than the other. Maybe we're moving forward, but we're slowing down. Maybe frictional force is bigger. Frictional force can be bigger. It just means that we're moving forward, but friction is slowing us down. Okay. Let's set up our coordinate system and then our t-chart. X, Y. Sum of the forces, X equals MAX. Sum of the forces, Y equals MAY. Great. What forces are in the x direction? Well, we have F1 is causing us to move forward, but frictional force is causing us to move backwards, so we're going to make it negative. That's equal to MAX. Fn is moving us upwards, but Fg wants us to move downwards, and that's going to be equal to MAY. But again, this box is not flying. It's not going through the ground, which means our acceleration in the y direction is equal to 0. So that means Fn minus Fg is equal to 0, which if we solve this equation, we can add Fg to both sides, and we get that Fn equals Fg. This is going to be very useful for us. Let's go to the x side, because the x side is really what we're concerned about. X side, we know F1. F1 is 30. So we can go ahead and plug that in. Minus f of f. What is f of f? Well, f of f has an equation. If you remember our equation for the frictional force from last time, it was called mu Fn. Oh, okay. We have Fn, but we don't know what it is yet, but we can find it over here. Fn is equal to Fg. If you remember, Fg has its own equation, mg. So we're going to take our mass and multiply by 9.8, which goes to 196. And so if Fg equals 196, that means our normal force is 196. So we can plug in it over here. Mu is 0.25, as given right here, the coefficient of friction, same thing as mu. And our normal force is 196, and so we multiply them, you get 49. So it means our frictional force is 49 newtons. Our mass is 20. We're looking for acceleration. And now I'm going to erase a little bit so we can solve. That means 30 minus 49, which is negative 19, is equal to 20 times AX. AX equals negative 19 over 20, which I don't know what that is. Let's go ahead and put the calculator. AX equals negative 0.95, if I can write it well. Geez, okay, 0.95, negative 0.95, which should make sense because our frictional force is bigger than our applied force, and so we should be slowing down. We should have a negative acceleration. Okay, and that's it. Let's do another one. Things are going to get a little more complicated. We have a 30 kilogram wagon pulled at a force of 50 newtons at an angle of 60 degrees to a horizontal, so no friction. So let's say we have a wagon that has a weight to it. It has a normal force, but it's being pulled at an angle of 60 degrees. And this is our applied force of 50 newtons. And we want to find acceleration. This is where things get a little bit weird because that F1 force is in both the x and y direction. And so that's when we have to remember to split the components. And so what we will often do with these is we will draw a second free body diagram called a working diagram, okay? We will draw a second free body diagram where we write components only in their component form. So instead of writing F1 again, I'm going to say that F1, if we split it into components, it has a component upwards and it has a component sideways. And of course, if you remember how to find components in the x direction, we use cosine theta. And components in the y direction, we use sine theta. Pause for a second. Realize Fn is up, Fg is down, F1 is at an angle, and so we need to split the components. F1 sine theta gives us the y component that goes up. F1 cosine theta gives us the x component that goes to the side. Okay. Once we have our working diagram, we can go ahead and do our XY chart. Sum of the forces equals MAX. Sum of the forces in the y direction equal MAY. In the x direction, we have only one force, F1 cosine theta equals MAX. And in the y direction, we have three forces. We have Fn plus F1 sine theta minus Fg, which looks complicated, but thankfully, we remember that this wagon's not going to fly. This wagon is not going to sink through the floor. AY is going to be 0. And so we don't really need to worry about the y side unless we need the normal force for some reason. So let's just look on the x side. The x side, we have F1 is 50. Cosine of 60 is 1/2. It should be 0.5 when you put it in a calculator. Cosine is 60. I'll double check it right now. Yep. And then our mass is 30 times our acceleration in the x direction. So our acceleration in the x direction is, 25 divided by 30 should be 0.83 meters per second squared. We didn't actually need to do the y side because we already knew the acceleration there. Sometimes we will need to do the y side in order to get some information, like we did on this last problem. We didn't need the y side to get the acceleration, but we needed the y side in order to get the normal force, because we use the normal force in our frictional force equation. On this one, we have friction, and so we're going to need to find the y side. So let's do one with friction. This is as complicated as we're going to get today, which I realize this is very new. This might be kind of hard today. That's fine. Practice. Do the assignment. Come to tutorials. Look online for other help on how to do these kind of problems. Again, we have a box, force of gravity down, normal force up. This time we're still pulling at an angle of 60 degrees. I'm trying to keep it consistent for y'all so we can see the pattern. So we'll call this F of 1. But this time we do have a frictional force. Mu is 0.25. And so let's draw a frictional force backwards. Again, friction force is always parallel to the ground. So frictional force will never be at an angle. Secondly, after we do our coordinate system, we want to do a working diagram again. Again, F1 is at an angle, and so we want to split its components up. So we have Fg down, normal force up, frictional force this way, and let's go ahead and split the components. F1 sine theta, F1 cosine theta. Okay, split the components up. That way, now you can see all those arrows are in a particular direction. They're either in the y or x direction, and so that makes our t-chart work for us. X, y. In the x direction, there are two forces now. Well, hold on. I'm skipping a step. I'm being a bad student. Sum of the forces in the x direction equal MAX. Start with our Newton law. Newton says this. Now in the x direction, what are the forces? Well, we have F1 cosine theta going in the positive direction and the frictional force in the negative direction. In the y direction, we have normal force and sine of F1 minus Fg. And of course, the acceleration in the y direction is 0, like normal. That will always be the case. I'll tell you it's not. Well, if you look on the x side, you'll realize again, we have frictional force, which means we need to find normal force. If you ever have frictional force, you need to find normal force first. So let's go ahead and do the y side first. Let's solve for normal force. Normal force is equal to, well, let's add Fg to the right side and subtract F1 sine theta to the right side. Take a second to follow that algebra. We're moving Fg to the right side by adding it, and we're subtracting F1 sine theta to the right side. Okay? And we know all these things. We know that Fg is equal to mg. So it's equal to 30 times 9.8. So 30 times 9.8 gives us 294. Minus F1 is 50. And sine theta, sine of 60 is equal to some value. It's like 0.8666, something around there. So 294 minus 50 times sine 60. I got 250.7 for my normal force. Notice, normal force is not always equal to gravitational force. It oftentimes is. Normal force, like we did on this problem over here. This is often the case, but it's not always the case. And so we need to make sure we always do the math and we look at the y side, because the wagon is doing a little bit of the help. The wagon is being pulled up a little bit. And so it's making gravity it's making the normal force not have to work as hard. Okay. And so we have the normal force now, so now we can plug in everything to this side. Let's go ahead and find the frictional force. It's equal to mu, the normal force, which is equal to 0.25 times that 250 we just found. And so I got 62.67 newtons. So when we plug it into the equation, we get F1 cosine theta, so 50 times cosine of 60 minus 62.67 is equal to 30 times AX. We simplify that, 50 cosine 60. Again, that should be 25. We're going to subtract our frictional force. We get negative 37 equals 30 times AX. And so we divide by 30 on both sides to solve for A. So AX is equal to negative 1.256. It's a lot of work per problem. Not all the problems will be like this. We'll have a lot of conceptuals, and the test is going to be a little shorter, but it is time consuming. But with practice, this won't take super long. This will take, a couple minutes, and so you'll be able to get it through a few. You need to practice. You need to be able to do this, especially the problems today. The problems today are going to be a bit easier than some of the other problems. And so it takes a lot of practice. It takes a lot of viewing videos. It takes a lot of coming to tutorials to really understand this. Some of you guys will get it the day of and will be able to just keep going and go through working the problems. Some of you are going to take a while. So make sure you do the practice in order to get it done. All right. With that, I'm going to end this show. I'll leave the last example. If you want to come to the tutorials, I can go over this last example with you. This one, it just changes up a little bit. Instead, I give you the acceleration, we're applying the same force. But you do all the work the same. You still set up everything, you do this, but instead of plugging in one of the forces, it's going to be something you're solving for instead. And you plug in the acceleration as 7 for AX. So AX in this case is going to be 7 meters per second squared. And then you can solve for the applied force. With that, please come to tutorials. I have them Tuesdays and Thursdays. You need to let me know ahead of time if you're online that you want to come so that I can get on Zoom to talk to you. Good luck. Have a good day.